So this is an example of a problem involving multiple random variables. Assume we are in a warehouse setting where we have two locations. We have location A and location B, and we want to prioritize which location to replenish first. So we have a initial inventory, an inventory quantity. So let's say that there's 50 units of some item in location A, and in a given hour there will be some amount of picks, so items being removed from the location to ship out of the warehouse, and that's represented by this X here. And there will be some items put into the inventory called put away, and that's denoted by Y here. So we have this process where we have some amount of items in a location, and some items get removed due to picking, and some items get inserted due to put away, which usually comes from the inbound side. And both of these are random variables because obviously the amount of picks and puts that might happen in a given hour can vary a lot or a little depending on the context of the location and kind of a bunch of different factors. And those sample distributions are given over here. So this represents the distribution of picks for both of these locations, and the two distributions for puts. And we want to, the main problem is which location has a higher probability of being less than or equal to 0. In other words, what is the probability that within the next hour this location will run out of inventory? And we're just going to use that as a measure of quote-unquote risk, basically risk of running out of an inventory, so we can kind of prioritize which locations we wanted to replenish first. So you can imagine that if we had a warehouse with like 10,000 locations, this is just one example of like a dummy algorithm you could write to like build a prioritization algorithm for which locations to consider replanning. And of course, there's a lot more nuance to that in real life, but for this dummy example, this is what we're going to work with. So basically, we want to compare what's the probability of A being less than or equal to 0, and what's the probability of B being less than or equal to 0. And basically we want to say which one is higher. Whichever one is higher, that's the one we want to consider replanning first, if we need to. So once we solve one of these, the other one will kind of be plug and play. So let's just focus on A for now. Actually, let me rewrite that again. Also, bear with me with my handwritten mouse. It's kind of challenging to write freehand with a mouse. But anyways, so let's expand this to the probability of 50 minus x naught plus y naught less than or equal to 0. And we can move this 50 to the other side. So we have, this is negative x naught plus y naught is less than or equal to negative 50. And then we can rearrange this inside as probability of y naught minus x naught less than or equal to negative 50. And what to think about here is that this is kind of a special case of a convolution. It's not really a special case, but if you have a sum of random variables, so if you had like x0 plus x1 plus whatever plus xn, this is usually called a convolution, where you are summing a bunch of random variables. And usually if the two variables come from the same distribution, there are usually convenient properties, kind of in general, and I won't go too deep into this for the sake of time, but in general, if you have two random variables, let's say x and y, the product of their moment generating functions, oops, oh, what happened? The product of their moment generating functions will represent the sum, or it will be the moment generating function of the sum of those variables. And so you could use this to determine what distribution it is. And usually, at least in most cases, it's kind of easy to see after you take the product of these two. Then you can kind of see what the parameters of the sum, of the distribution of the sum would be. And if you're interested, I would recommend looking up the relationship between sum of random variables, or convolution of random variables, and the product of their moment generating functions. But at least in the case of a normal distribution, if we have a normal distribution with mean mu naught and variance sigma naught, plus a normal distribution with mu 1 sigma 1, then this would give us the distribution where the mean is mu naught plus mu 1, and then the variance would be sigma naught plus sigma 1 squared. And I'm not going to prove this here, again, for the sake of time, but if you were to look at the moment generating function for this, and you take the product, it's pretty easy to see that these properties would hold. But we will be able to use that here, because since y0 and x0 are normal distributions, this actually boils down to a convenient form where y0 minus x0 actually follow the distribution of 10 minus 35, which is negative 25. And then their variances squared, or the sum of the variances. This I wrote down. With standard deviation. So 15 is actually the standard deviation, not the variance. So in this case, it would be 5 squared plus 15 squared. Sorry, my brain wasn't working. And then the square root of that. So this is the standard deviation. This is the mean. And then we want to see the probability of this being less than or equal to 50. And if you kind of try to look at this on the graph, you know, if this is minus 50, and you know we have some function here, the probability of being less than or equal to this is just the area under the curve from whatever lower bound. In the case of a normal distribution, this is from negative infinity to negative 50. And as you might notice, this is pretty much the definition of the cumulative distribution function. So we want to get, we're checking if the probability is less than or equal to some value. So really, we are checking the cumulative distribution of this at 50, and that will give us the area under the curve there. So if we go into SciPy here, or into a Jupyter Notebook, here I'm just using like a temporary notebook. I'm going to import SciPy, the normal distribution, and I'm not sure if I'll need NumPy, but I'll just import it anyways. All right, and then with this, we can get the norm.cdf. So our distribution, well, first we want the value -50. So the value is -50, the loc is -25, and then the scale is 5 squared plus 15 squared, and that's under a square root. And so that is 5%. And then we could do something very similar, except, see now, B is pretty much the same exact case, except instead of 50, it'll be 70. So this will be -70. And of course the distributions are different. So let's just write that one down. So y1 minus x1 follows a 22 minus 55, what is that, -33, I believe, if my, I'm very bad at mental math. And then the variance is 8 squared plus 20 squared. 22 minus 55. Let me just make sure that is right, because I'm second guessing myself. Okay, just want to make sure that's actually right. So this is -70. This is -33, and then this is 8. And what was the other one? 20. Yeah, 20 squared. And this is 4.2%. So in this case, location A has a slightly higher risk, granted a pretty low risk, but a slightly higher risk of location B of running out of inventory. So if we wanted to trigger a replen, we would want to prioritize location A first, since it has a higher risk of running out of inventory. And that is one example of solving problems that involve multiple random variables. In this case, we got to use a little bit of convolution and properties of sums of random variables. And again, if you wanted to get more into the theory behind that, you can look into the products of moment generating functions between random variables, and that will show you some really cool properties when taking sums. But hopefully that's helpful, and maybe you learned something, maybe you didn't, but that's all.